If you spend enough time reviewing academic papers, you will eventually find a methodology error so common and so severe that it immediately invalidates the entire study. It usually looks like this. The researcher runs a test, looks at the math, and writes, "The null hypothesis is confirmed." Writing those exact words means the author has completely misunderstood what a statistical test actually does. We have two buckets of hypothesis testing. First is the null hypothesis, H0, the default state of no effect. The second is the alternative, H1, what the researcher suspects. The absolute law, math only evaluates the default state. It never proves H0 true. It either rejects or fails to reject. Failing to find evidence of a change is not the same thing as proving that no change exists. Getting that distinction right is what separates a defensible result from an overclaimed one. Let's pull this out of the classroom and put it into a security operations center, where these exact mathematical rules govern live threat detection. Our security team has historically taken an average of 42 seconds to detect a specific attack pattern. That 42 seconds is our default baseline. This scatter plot shows what happens when the team deploys a new detection rule and times the next 25 attacks. The math spits out a p-value of 0.07. The p-value is the probability that we'd see this exact data by pure chance. The standard threshold for action is 0.05. Because our result of 0.07 falls above that line, we failed to reject the baseline. When this happens, researchers are often tempted to move the goalposts. They retroactively relax the threshold to 0.10 just to force a statistically significant result. This is called p-hacking, and it completely compromises the test. The honest conclusion here isn't that the new rule failed. It's simply that a sample of 25 timed detections was not large enough to separate a genuine improvement from ordinary background noise. The correct next step is to collect more data. Because statistical tests rely on probabilities rather than absolute certainties, they can fail in exactly two specific ways. This matrix lays out the risks. The top right quadrant represents a type 1 error, or a false positive. This happens when you reject the default assumption even though it's actually true. In a security center, this is identical to an intrusion system firing a false alarm. The bottom left quadrant is a type 2 error, or a false negative. This is when you fail to reject the default assumption, even though it's actually false. Operationally, this is a system missing a genuine attack. Now, a manager trying to avoid false alarms might decide to implement a very strict significance threshold, moving the alpha level from the standard 0.05 down to 0.01. The math forces a direct trade-off here. By shrinking your chance of a type 1 error, you automatically expand your chance of a type 2 error. Cutting down on false alarms guarantees you will miss more real attacks. Choosing a statistical significance threshold is a calculated risk management decision. Tuning a math formula is identical to tuning a security perimeter. Passing that threshold and achieving statistical significance is only half the battle. Standard testing has a massive blind spot. A p-value only measures probability against random chance. If you use an aggressively large sample size, you can make a microscopic, practically useless difference appear highly significant on paper. To fix this, you have to measure effect size, often calculated as Cohen's d. This answers the exact question a p-value cannot. How big is the actual difference? Researchers use a standard scale to read Cohen's d. A score around 0.2 is small, 0.5 is medium, and 0.8 is large. This side-by-side comparison shows why you need both metrics. Both of these test results have an identical p-value of 0.03, but the left side has a tiny effect size of 0.08, while the right side shows a massive shift at 0.71. They are equally statistically significant, but only the right side is operationally worthwhile. Failing to reject is not confirming. The p-value tells you if a change is real, but the effect size tells you if it actually matters.